I'm going to talk about turbulence in the relativistic plasma. So this work is done in collaboration with Christian Vega and Vadim Reuterstein, who should be credited for the numerical analysis, which I'm going to show you. So, so before I start, I would like to mention that this turbulence in the relativistic plasma is, of course, different from our convention. Alfvénic turbulence in conventional plasmas. However, there are some similarities, and I would like to build upon this and see how, using these ideas which were developed in the non-relativistic case, one can describe relativistic plasma. So turbulence plays a role, or is thought to play a role, in various astrophysical environments. Some of them are listed here. So, and even if we do not discuss how turbulence accelerates particles, by itself, it's a very non-trivial problem, how to describe strongly nonlinear turbulent dynamics. And we will see what complications, or maybe simplifications, come from the relativistic case. So this slide shows some examples how turbulence can accelerate particles, so how particles can be accelerated through high non-thermal energies in some astrophysical environments. So, for example, there are some standard mechanisms how particles can gain energy by interacting with turbulent structures. So, for example, if we have collisionless shocks, they can accelerate particles which bounce back and forth across the discontinuity. So, or you can have, so this is, or you can have stochastic scattering by randomly moving magnetic structures, which can also reflect or deflect particles. Then another standard mechanism is magnetic reconnection, because a magnetic reconnection is the only place in ideal plasma, in kind of nearly ideal plasma, where electric field can be strong, can be large, and therefore electric field can just accelerate particles along the, if also there is a guide magnetic field, along the background magnetic field. So this is kind of not stochastic acceleration, but still an important mechanism of particle acceleration. So, and more recently, it was discovered in numerical simulations by several groups, which are listed here, that magnetic turbulence, especially magnetically dominated turbulence, can also provide an official mechanism for particle acceleration. So, so magnetically dominated means that magnetic energy associated with the guide field and with the fluctuating field is much larger than the rest mass energy density of plasma particles. So, and in this, and also I will be concentrating on the ultra-relativistic regime. And in this regime, it really doesn't matter what plasma we're dealing with, meaning if energies of particles are comparable, then the numerical simulations which I'm going to present will be conducted for pair plasma, for ultra-relativistic pair plasma. So now let's talk about how one can set up Alfvénic turbulence. So, so one can do it numerically in different ways, and also in nature it can be generated in different ways. So, for example, one can initialize some initial particle distribution. One can assume that it is non-relativistic, or relativistic, or ultra-relativistic. One can assume that it is isotropic or anisotropic. One can initiate large-scale fluctuations of fields, or in this turbulence, say, of magnetic fields. Turbulence can be decaying. You can just provide some initial perturbations and let it evolve in time and see what turbulence will be generated in this process. Many numerical simulations use this approach. Or it can be driven, so you can drive those plasma flows at large scales and let them become unstable and generate turbulence and generate turbulence cascade. So you can assume that your equation of state is compressible, or you're dealing with compressible or incompressible medium. So then one can discuss what magnetic guide field this system has. So one can envision a situation where fluctuations at large scale are so strong that they're much stronger than the magnetic flux which permeates, say, your simulation box. Or you may assume that fluctuations are much weaker than this flux, in which case you will have a strong guide field, turbulence where you have strong uniform background magnetic field imposed onto the system. Then, since this turbulence will convert energy of collective fluctuations into plasma particles, plasma will be heated. And if there is a lot of energy in initial magnetic fluctuations, you can heat plasma significantly. Then the question whether plasma can be cooled by some radiative processes or cannot be cooled, meaning you have to compare the times, radiative time and heating time, also becomes important. So in the first case, if you have an efficient radiative coolant, you will not be able to significantly heat. You may not be able to significantly heat the plasma. In the second case, plasma will be heated as you run your simulation. Then what numerical simulations show that the turbulence spectrum, the distribution of energy of magnetic fluctuations over scale, is universal, surprisingly universal. And typically, it's not sensitive on how you drive your turbulence on the large scale. So that's what we mean when we say that turbulence is a universal phenomenon. It has universal Kolmogorov-like spectrum. So we basically refer to this property that somehow fluctuations at small scales forget about large-scale conditions, and you have a universal distribution of turbulent fluctuations. But what I'm going to argue, so the particle acceleration may be sensitive on some properties which you cannot see in the turbulent spectrum, some kind of structures or how you drive at large scales and so on. So now one can ask, what is most important conditions that we should care about? And it turns out, and I'm going to argue and show numerical simulations, that it is whether the guide field imposed on the system is weak or strong. So whether your fluctuations immersed into very strong background magnetic field, or whether background magnetic field may be neglected as compared to the strengths of the large-scale fluctuations. So it turns out to be the most important conditions. So if your plasma is magnetically dominated, magnetic energy is much larger than the energy of the particles, then it turns out that if you tell me the ratio of the large-scale magnetic fluctuations to the large-scale guide field, I can tell you what is going to happen to the particles in such turbulence, the spectrum of particle distribution. Okay, now some parameters. And first I describe what simulations we are going to consider. I will show you some numerical results. So we will consider decaying runs. We will assume that initial distribution of particles is non-relativistic or mildly relativistic and isotropic. We can initialize particles with, say, Maxwell-Hüttner distribution or some other distribution. It doesn't really matter because it's kind of non-relativistic. We assume that we have decaying turbulence, and we assume that there is negligible radiative coolant. So when initial fluctuations evolve, they will hit plasma. So plasma will be heated up to some non-thermal and relativistic temperatures. Okay, now parameters. So I already mentioned that we will be dealing with plasma with some imposed large-scale magnetic field. So, and then we will measure the strength of the magnetic field, comparing it with the strength of the large-scale fluctuations. So we will initially consider the case where the guide field is very large, in this limit, and then discuss what happens when guide field becomes not that large, comparable to the fluctuating part of the magnetic field. So this way it will be easier to describe the important processes which will shape the particle distribution function. Now we can introduce two magnetization parameters. It's kind of commonly done. So first magnetization parameter is the ratio of the magnetic energy density to the this is the enthalpy of initial particle distribution. So basically it's magnetic energy over the energy associated with particles. So we assume that this parameter is much larger than 1. And the other parameter, which is associated with, which measures how strong the magnetic fluctuations are, is also much larger than 1. So it's a magnetization parameter. Now, in here we have first a place where analogy with the non-relativistic case becomes quite interesting. So in the non-relativistic plasma, there is a parameter which is somewhat similar to the magnetization parameter. This is the ratio of the, say, electron cyclotron frequency to the electron plasma frequency in a non-relativistic plasma. So in conventional plasmas, this parameter is always much, much smaller than 1. In laboratory plasmas or space plasma, it's always much, much smaller than 1. So in the non-relativistic case, this parameter has a special name. It's called a quasi-neutrality parameter. So when this parameter is much smaller than 1, your plasma fluctuations are quasi-neutral, meaning that the fluctuations of the negative charge and positive charge balance each other very well. So the difference between those densities, fluctuation of positive and negative charges, is much, much smaller than those fluctuations themselves. However, even if you consider a non-relativistic case and ask formally what happens if this parameter becomes comparable to 1 or much larger than 1, then you immediately see that you will recover similar properties similar to the relativistic turbulence. So plasma will become non-neutral. So fluctuations of plasma charge will become non-negligible. It will be important that non-neutral locally on the fluctuating level. Of course, generally plasma is neutral. Okay, so now let's suppose that we set up some initial perturbation of, say, magnetic perturbation and let it evolve. So those magnetic perturbations will try to relax, drive plasma flows, right? And if they drive plasma flows, they will drive turbulence. So we may assume that initially the energy which is contained in magnetic fluctuations is much, much larger than the thermal energy or the kinetic energy or rest mass energy of plasma particles. And when we drive those fluctuations, we can assume, kind of naively, assume that they will drive ultra-relativistic kinetic fluctuations on the plasma. However, this doesn't happen because even when we heat plasma to relativistic temperatures, the speed of sound in the plasma is non-relativistic. So V squared over C squared is about 1/3 for the, say, isotropic distribution of plasma particles. Therefore, the situation is somewhat similar, and it was realized in numerical simulations before, like several years ago, that when you drive such flows, you will create those flows as in a supersonic turbulence. They will create shocks, structures will dissipate energy quite significantly. So as a result, in about 1 turnover time, in about 1 large-scale crossing time, you will have a plasma which bulk flows are mildly relativistic, but whose temperature is ultra-relativistic. So all this initial energy of magnetic fluctuations will convert into thermal energy of particles very rapidly, leaving bulk fluctuations at some non-relativistic level. And this is the results of numerical simulations. It was 2-dimensional and 3-dimensional simulations. So first plasma velocity increases, but once it reaches about like 1/3, when V squared becomes like 1/3 of C squared, the bulk velocity starts to go down. And in this case, you basically convert significant fraction of initial magnetic energy into plasma temperature. So plasma becomes ultra-relativistic. So if we have plasma turbulence where bulk flow is mildly relativistic, but plasma is ultra-relativistic, so as the first of the kind of zero-third approximation, let's try to describe this plasma using non-relativistic equations of motion, but we assume that the equation of state is ultra-relativistic, right? So that's what we're doing. So one can describe it analytically, but I'm not going to write a lot of formulas, so I will just show you the results of the simulations. So this is the numerical simulations of the spectra of magnetic fluctuations, which is blue line, spectra of electric fluctuations, red line, and this is paraelectric fluctuations, which are weak, so just we concentrate on magnetic and electric fluctuations. So as was mentioned by Andrei, so when we have, in the ultra-relativistic case, there is also a strong guide field. Fluctuations of energy contained in the magnetic fluctuations is comparable to the energy contained in the electric fluctuations. But energy associated with the bulk kinetic plasma motion is negligible. So here we have an important difference with the non-relativistic case. So in the non-relativistic plasma, when we write equations of motion, we write them for the magnetic fluctuations and velocity fluctuations. For example, that's what is done in MHD. Right? You can ask, what about the electric fluctuations, which are also present in such a system? Well, the energy contained in the electric fluctuations is negligibly small in conventional plasma. So here, the situation is reversed. So most of the energy is contained in the magnetic fluctuations, the electric fluctuations, but energy contained in the bulk kinetic fluctuations is negligible. So all the energy is magnetic and kinetic, that's what is shown, and total energy is shown by this blue line. Yeah.
So since you're using non-relativistic equations for this, so this difference arises purely out of using it in equation state.
Yes, but I mean, you can write the equation for...
Can you repeat the question?
So the question from Alex Chikachikhin is that when you use non-relativistic equations of motion, where the difference arises purely from the equation of state. Yes, and also instead of plasma, kind of mass of the plasma fluid, you substitute some parameter which is related to enthalpy.
So you're saying I change 5/3 to 4/3?
No, not only that, not only that. I'm saying plasma mass of particles also is not just rest mass of particles, but also has some corrections.
Where does it come into the non-relativistic equation?
Non-relativistic equation, instead of mass in the denominators, you will have not mass, but mass multiplied by enthalpy.
I see. So that's what does it.
Yeah.
Not the equation of state.
Equation of state plus some, yeah. Okay, now, so if we look at this spectrum of turbulence fluctuations, we see that we have kind of Kolmogorov-like cascade, and then there is some breakpoint at the inertial scale, approximately inertial scale of plasma, which is expected, after which spectrum becomes steeper. But then, of course, the question arises, what is the inertial scale in the relativistic plasma? So, once again, contrary to the non-relativistic case, when we define the inertial scale, we have to discuss what plasma modes we consider. So for different plasma modes, the inertial scale is different. So if you consider Alfvénic modes, this is your inertial scale. Here is enthalpy of the associated with particle distribution. If, for example, you consider ordinary mode, which somewhat has dispersion relation kind of similar to the Alfvénic mode, then the then the inertial scale is not just c divided by omega p, but gamma factor and enthalpy enters differently in this equation. So there is no unique inertial scale in such a plasma. It depends on the mode that you are studying. So here we study the Alfvénic fluctuations, and this is the inertial scale associated with Alfvénic fluctuations. So we expect that this turbulent cascade will be terminated or modified at this inertial scale, relativistic inertial scale of the plasma. However, more and this slide shows typical kind of typical scaling of magnetic fluctuations associated with Alfvénic turbulence. So at large scales, fluctuations are delta B naught. Then at smaller scales, fluctuations become weaker, proportionally to some power of the scale. It may be from 1/3 to 1/4. So here it's close to 1/4 in the simulations. And there is also critical balance condition saying that the typical scales of the turbulent eddy in the direction along the background magnetic field and in the perpendicular direction are related proportional to the scales of ratio of fluctuations to the guide field. Okay, now, next question. So cascade gets modified, or Alfvénic cascade terminated at the inertial scale. But the question is, so more refined calculations shows that, in fact, maybe I'll just, this slide I already basically said that. So more detailed fluctuations say that it may be not the case. The cascade can be terminated at scales slightly larger than the inertial scale. And this can happen due to two effects. So in the non-relativistic case, it's been suggested that cascade can be terminated by the tearing effects. So it doesn't get to this scale, to all the way down to the inertial scale, because it gets disrupted by the tearing instability. So Alfvénic turbulence creates sheared magnetic structures, and those structures may become unstable due to tearing instability, which can modify or disrupt the Alfvénic cascade. So same is true in the relativistic case. So the scale at which cascade gets disrupted by the tearing instability is larger than the inertial scale by this factor. So this factor may be, once again, depending on the separation of scales, it can be small or it can be, significant. So, however, in the relativistic case, there is another scale which may compete with this tearing scale. It's a so-called charge starvation scale. So where the scale comes from? Well, if we consider the current density associated with Alfvénic structures, the smaller the scale, the larger the current density. However, current density cannot be infinitely large because the velocity of electrons is limited by the speed of light. So at certain scale, plasma will not be able to sustain that strong current. And then cascade should be modified in this case. Simply cascade cannot continue, Alfvénic cascade cannot continue beyond the scale. So this is a typical scale associated with the tearing instability. This is the typical scale associated with the charge starvation phenomena. And it depends that in the relativistic case, it's not always obvious which scale wins, which scale is larger. So for example, this analysis in a recent paper by Demidov and Lubarsky, they did some analysis for the pulsar wind nebula and concluded that it's not clear which scale wins. So one cannot say just from some estimates, both scales may be important. However, when they consider AG and jet, they claim that it's probably Tirin instability which comes into play before the charge starvation comes into play. So there are these scales which, the bottom line that they can increase a little bit the scale where the Alfvénic cascade gets terminated. Okay, now what happens at such scales? So this explains why Tirin instability can terminate the cascade. So this slide shows some old numerical simulations of Alfvénic turbulence. So assume that the guide field is sticking out of the board. Those are fluctuations in the direction normal to the guide field, magnetic and velocity field. And you see the turbulence creates these structures, shear structures, that can become unstable because they look like current sheets. They may become unstable to the Tirin instability. And then the question is, which rate is larger? The rate of the turnover rate of those turbulent structures or the rate of Tirin instability? And as scale goes down, the rate of Tirin instability becomes larger at some scale, and that's where you disrupt your turbulent cascade due to Tirin instability. So charge starvation, when current becomes too large, approach this value, this plasma cannot maintain this current, as we already discussed, and cascade should be terminated at this scale. So in the natural question, what happens at the scale, scale where charge starvation effects come into play? It's a very interesting question, and to approach it, let's look at the equation in one of the Maxwell's equations. But I have rewritten it as an evolution equation for the electric field, right? So if gradients of the magnetic field become large enough, current is not able to maintain, to compensate for this curl of the magnetic field. Then it means that the electric fluctuations become non-negligible. It means that the displacement current, fluctuations of the displacement current become essential in this system. And therefore, the parallel electric field may increase. However, if the parallel electric field increases in say, laboratory frame, if parallel electric field becomes non-zero, it also remains non-zero in the frame associated with the motion of the plasma, because of the invariant, right? If parallel electric field becomes non-zero, then frozen-in condition breaks down. So magnetic field lines are not frozen any longer. So when you see something analogous to magnetic field lines start slip through the plasma, they not follow the plasma motion. So magnetic gradients become reduced, and you can even trigger reconnection probably in this way, in the same way as reconnection can be triggered by the inertial effects, when plasma particles cannot follow the fluctuations of the electric field. Also, numerical simulations by several groups here show that in this case, energy cascade also get modified. So if you look how energy gets distributed over parallel k-perpendicular directions, some energy starts flowing in the k-parallel direction rather than k-perpendicular. So energy cascade also somewhat gets modified. But one could probably expect in this case that since parallel electric field increases, you can also contribute to the particle acceleration. It can contribute to energetics of the particles. So in this slide basically summarizes what happens at those scales. So if the cascade is terminated by Tirin instability at scales smaller than the Tirin scale, energy spectrum becomes steeper, either -3 or -8 depending on which model for the current sheet you apply. So in case of the charge starvation, the spectrum of energy cannot be flatter than -3. So in order to ensure that current does not grow at small scales, the spectrum of the magnetic fluctuations should be steeper than k to the -3. So we expect here indeed that the spectrum will steepen to or below k to the -3. So very similar to the Tirin in some sense, Tirin stability. Okay, so that's about Alfvénic turbulence. Now let's move on and discuss what happens to particle acceleration. How particles, yes? Yeah.
Saying it systematically happens at higher k-perp than the tearing, or?
So Landau damping in this case, so this scale here is where Landau damping becomes very strong. So, but all these effects which I discussed before happen at scales above z, so above the scale of Landau damping. Yeah, yeah. Okay, now what happens to particle acceleration? So what particle acceleration mechanism are typically discussed, and we're also going to discuss those mechanisms. So it can be parallel electric field, as we just discussed before. So when you have Alfvénic turbulence, it reaches a small scale, parallel electric field appears, either due to tearing effects or due to charge starvation effects, and you can accelerate particles. Then there may be curvature acceleration. Particle can be accelerated when they follow a curved magnetic field lines, and if all this magnetic structure is moving, it's like a particle kind of gets reflected from a moving wall, and its energy increases. Or there can be mirror acceleration. Particle can also be reflected from regions where magnetic field is strong. However, what is in kind of my view, in our view, when we discuss this, did these numerical simulations, it seems that an essential question here is what happens to the magnetic moment during this acceleration process. So, in this question has, two motivations why this question is important. First of all, if we want to understand synchrotron radiation, which comes from fast particles, if magnetic moment is conserved, you cannot increase particle gyro radius when particle gets accelerated, because magnetic moment is essentially flux which goes through the particle gyro radius. Then you can accelerate your particle only along the background magnetic field. So you increase the parallel component of the momentum of the particle, keeping perpendicular component constant, meaning that pitch angle becomes smaller during this acceleration. And if pitch angle becomes smaller, obviously it affects synchrotron radiation, which is quite sensitive to the sign of the pitch angle, right? So it's first question. So it's indeed an important issue if you want to interpret or predict radiation from such accelerated particles. But second question is also important. It's also quite crucial for analytic modeling. Because if you think about these mechanisms, curvature acceleration, mirror acceleration, when we discuss those mechanisms, we implicitly assume that the magnetic moment is conserved. Otherwise, it doesn't make any sense to talk about curvature acceleration or mirror acceleration. Those are mechanisms for particle, those describe particle motion where their magnetic moments are conserved. That's why particles follow magnetic field lines, that's why they get reflected from magnetic mirrors. So then this question, what happens to magnetic moment, is a fundamental issue here, and that's what I'm going to address in the next slides. So what numerical simulations show? So when you have turbulence with weak guide field, first of all, as we discussed, you show that particles get accelerated, but they accelerated mostly along the background magnetic field. So this slide shows the kind of distribution of particles over parallel momentum and perpendicular momentum. And you see that a lot of energy kind of spreads in the parallel direction, but not in the perpendicular direction. So you accelerate the particles, and you create the population of energetic ultra-relativistic particles with very small pitch angles during this acceleration, which is consistent with what we see. So parallel electric field, even weak electric field, is present in Alfvénic fluctuations. It becomes large when we get to close scales, and then this field, in principle, can contribute to particle acceleration along the background magnetic field lines. Okay. So one can estimate kind of the absolute minimal electric field which just exists in the Alfvénic wave. If particle goes through this Alfvénic structure, it gains some energy, so its gamma factor increases, and you can calculate how this energy will increase, and this kind of scaling how this energy increases if particle encounters those structures randomly, so it's kind of random walk in energy, so delta energy is proportional to the number of events which accelerated the particle. So that's what numerical simulations show. So indeed, initially, when particles get accelerated, you have something which is probably provided by the I don't have much early time, it's up to 8. But before that, you see kind of tails which may be indeed related to acceleration by the parallel electric field. Now, next point. What about the acceleration by the curvature, by plasma curvature? Magnetic field line curvature. So let's consider a very simple model. I assume that I have a magnetic field. So let's assume that the guide field is sticking out of this board. This is a guide field. And magnetic field line kind of goes around this there is guide field, and there is also magnetic fluctuations. And we're looking at the projection of this magnetic field line onto the perpendicular plane, right? And assume that the structure is moving to the left. So let's assume that the scale of the structure is lambda, the strength of the guide field is B naught, the strength of this fluctuation of this component of the magnetic field, which is responsible to this deviation from the guide field, is delta B perp. And then one can evaluate the curvature radius of the structure, the length of this path when particle travels along the structure. And you can calculate how much energy particle gains when it kind of gyrates along this magnetic field line and goes through the structure. So this is the answer shown here, where this is the traveled path, this is radius. So we see that when the structure becomes smaller and smaller, lambda goes to 0, curvature becomes larger, curvature becomes smaller, but so does the traveled path become smaller. So curvature accelerates particles significantly, acceleration is significant, but the path is shorter, and this kind of scale cancels out, and eventually you have this expression for the acceleration by curvature. So the increase in gamma factor is proportional to gamma. Therefore, I can write it as increase in logarithm of gamma. And so there's each interaction with curved structure gives a kick to the logarithm of the gamma factor of particles, right? And of course, the question here, what is the distribution of this curvature event? So here I assume that we're kind of dealing with a case where Gaussian random walk is applicable. So in each interaction, gamma factor increases slightly, and you have to accumulate many interactions in order to get some distribution, right? Of course, one can consider models where, for example, the curvature acceleration becomes very strong and they're not Gaussian, but it's more complicated to me. So to my purpose, I will consider kind of a Gaussian random walk. So that shows that the logarithm of energy increases proportionally to the square root of the number of interactions, and it's also proportional to delta B over B and the velocity of the structure. So this is the formula for how a logarithm of gamma factor increases with the number of interactions. And you see that it's proportional to delta B over B naught. So we see that the strongest interaction is provided by the largest eddies. They have smallest curvature, but they move fast. Now, what energy distribution we get from this random walk in the logarithmic space? Well, we get a log normal distribution, right? Because logarithm has Gaussian distribution. So and that's what numerical simulations show. So when we have a strong guide field and we evolve, we accelerate particles for quite a long time. Initially, you saw the picture on some previous slides. It didn't look like log normal, but eventually it approaches a log normal shape. So it seems to be consistent with what we expect, right? Okay, but now I would like to ask, but what about the angle, the pitch angle of those particles? And here is the measurement of pitch angle distribution of these particles. You see that particles have pitch angle is a cosine negative 101, so they're very, very closely aligned with the magnetic field lines. So indeed, even though we accelerated particles due to curvature by curvature acceleration, and this acceleration is provided by the perpendicular electric field, we accelerate the particles in the field parallel direction. So and this may be counterintuitive. So one can, for example, measure in numerical simulations what work is provided by parallel electric field, by perpendicular electric field, but it doesn't tell you yet whether you're accelerating particles in the perpendicular or parallel direction. So perpendicular electric field may absolutely, efficiently accelerate particles in the parallel direction. That's what may be happening here. So perpendicular, okay. But now, I would like to explain, okay, what happens? Let's say we keep accelerating particles. They become aligned with the background magnetic field more and more, so become stronger and stronger aligned. Can it continue forever if I'd like to accelerate particle to extremely high gamma factors? Does it mean that the pitch angle will become infinitely small? And the answer is no, because all our discussion of pitch angle based on the conservation of this magnetic invariant, P perp over B. So you increase P parallel, P perp becomes constant. However, this is only, yeah.
Just ask about this point about E perp versus E parallel. So presumably what happens is that your perpendicular electric field tries to accelerate the particles, and then your effectively the mirror force rearranges that in parallel direction. But that's ultimately parallel.
No,
right?
let me, no, it's perpendicular because, so we have this example which we give to students. Let's assume that we have a magnetic field line which looks like that, right? Particles goes from this direction, gets turned and goes back. And the structure is moving to the right. So particles go here, get reflected, go back, right? So initially, magnetic moment is conserved through this exercise. So eventually, particle will get parallel electric field, parallel magnetic moment. But what electric field accelerated the particle? Obviously, magnetic field did not accelerate particles. So when particle goes along this curved line, it also drifts in the direction perpendicular to this curved structure. And there is electric field in the perpendicular direction because of V cross B velocity. So this electric field acts on this drift of this particle in the perpendicular direction. And this work gets converted into this parallel magnetic moment. So it's work of the perpendicular electric field on the perpendicular motion of plasma, on the perpendicular drift of plasma particle. Okay, now, but pitch angle cannot be infinitely small simply because this expression for the magnetic moment does not hold for very small pitch angles. So instead, the expression becomes more complicated as you go to small pitch angles. And it was worked out by Little John in 83 for the non-relativistic case, 84 in the relativistic case. Jan Eggedal applied it to the solar wind. So instead, when P parallel grows to very large numbers, P perp cannot be smaller than this value, which includes the gyro radius of the particle and the radius of curvature. So then first, if you accelerate particles, pitch angle becomes smaller and smaller and smaller and smaller. When it reaches this limit, when P perp reaches this limit, this expression doesn't hold any longer, and pitch angle starts increasing after this moment. Even though the magnetic invariant is conserved, there is no pitch angle scattering. It's simply that magnetic invariant has a different form, different shape, where pitch angle doesn't have to be small. It's increasing. So, and that's what this analytic arguments show. So initially, let's say that initially we have some pitch angle theta naught. And we accelerate our particle. So initially, pitch angle goes down, inversely proportional to the energy, as it should. Then it reaches some point, after which it starts growing, simply because the shape, the form of the magnetic moment changed. And after this point, after this gamma star, after this energy, the pitch angle starts increasing. And I would like to stress that all this region is non-thermal. It has nothing to do with thermal, with going from thermal to non-thermal energy or something like that. So, for example, in our numerical simulations, this thermal energy is about gamma is of order of 6, but we see the saturation at gamma of order of 100. So it's a deeply non-thermal, highly ultra-relativistic region. So at this point, then pitch angle starts growing, right? And then it grows, and at some point, this pitch angle reaches the smallest scale of the Alfvénic eddy, inertial scale of fluctuations. At this point, it can resonate with this eddy. And you can get genuine pitch angle scattering in addition to acceleration process. And here, at this scale, gamma critical, you change to a different regime. Here, you already have pitch angle scattering. Here, magnetic moment is conserved. Right? Obviously, this may have implications for synchrotron radiation. So here, I would say that spectrum becomes kind of softer, and here spectrum would become harder as you go to such energies. So, and these are numerical simulations that demonstrate that. So, this is pitch angle. We kind of zoomed into these regions here. Consider very small pitch angles. And consider different energy intervals. So here, thermal energy is about 6. So 20 is already quite non-thermal tail. So the distribution of particles over angles is given by the blue line. Then we increase, look at particles at high energy. It's given by the red line. And surprisingly, it follows a nice self-similar shape. It kind of angle decreases following the self-similar law. But if you increase energy, if you consider even more energetic particles, gamma exceeding 100, pitch angle starts to saturate. That's where you hit this point, and that's approximately where it should be, according to analytical calculation, where you hit this energy where magnetic moment, the expression for the magnetic moment changes. Right? Okay, so and now if we continue, if you look at high energies, we eventually look at the critical energy where this gyro radius becomes so large that particles now can efficiently interact with turbulent fluctuations and may have pitch angle scattering. But once again, this may happen only if delta B, so so when pitch angle scattering becomes efficient. Okay. Now, in this case, if I evaluate this energy scale, it's going to be about 7,000. So in our numerical simulations with a strong guide field, we simply don't have particles, we simply don't have enough particles in our simulation to accelerate to such energies. We accelerate to about gamma equal 300 to 200, but not to 7,000. So this is, it's a strong guide field. Right? A strong guide field B naught is 10 times larger than delta B, and this is this scale which is shown here. It's about 7,000 in the simulations. Yeah. So we simply cannot. We can go up to here, but we cannot go all the way here because we simply, for the strong guide field, the energy distribution function of particles declines so fast that we simply don't have enough particles at such large energies. It's very expensive to run it to large energies. So, and therefore, the factor is 7,000, and we see particles are still very well aligned with the magnetic field. Now I'm moving to the case where guide field is not that strong. Now let's look at the case where guide field is comparable to the fluctuating field. And this is a plot which shows the pitch angle, the distribution of the pitch angle for plasma particles for different energies. You see that first particles are more or less aligned with the background magnetic field at small energies. But then at certain energy, something changes, and particles become kind of scattered more efficiently from the field line direction. And so for this case, when delta B over B is equal to 1, one can evaluate gamma C. It turns out for the simulation to be around 70. And that's where this change occurs. So when gamma is about 70, you see this green line where something starts to change in the distribution of your particles over pitch angles. Now, what about the distribution of particles? And this, I would just show another simulation from paper by Komisis and Cironi, who did it first, who actually considered those angles. And we just evaluated this gamma C parameter for their runs and found that gamma C is of order of 25 in their runs. And if you look at this plot, those squares or circles, that's where, so circles go to squares, that's there you start to see the change in the angle distribution function. So maybe it's also related to a similar effect. Okay, now what about the energy distribution of particles? So in this case, when we have a weak guide field, and when pitch angle scattering becomes very efficient, because gamma C parameter is quite small, we see power law distributions of particles. So if this factor is 25 or 30, somewhere here, gamma C, then we see kind of power laws in this particle distribution. So we believe, so as a conjecture, that this particle distribution is somehow related to the conservation of adiabatic of magnetic invariant. When magnetic invariant is preserved, is conserved, you get log normal distribution in very small pitch angles. But when you have a mechanism, when you reach large enough energies to break the magnetic moment, to provide so particle can interact with turbulent structures where pitch angle you could have pitch angle scattering, probably that's the regime where you start seeing power law distributions. That's a conjecture, of course, it's hard to trace it analytically all the way, numerical all the way. So, and then how one can, is there any way to understand it analytically and describe it analytically? Well, we can say, okay, what happens when you introduce a new picture pitch angle scattering? So basically say magnetic moment is conserved, particle can be accelerated by curvature drifts, for example, and then it encounters strong variation of magnetic field at the scale dE, where pitch angle can scatter. So what if you consider both acceleration of particles and pitch angle scattering? At some points, you have pitch angle scattering. Then if you have pitch angle scattering, then particles can be accelerated by magnetic mirrors. So particles with very small pitch angles just go through those mirrors without noticing them, right? You need to have some minimal pitch angle in order for a particle to be reflected from a magnetic mirror. You have to stay out of the loss cone on this magnetic mirror, right? So if you accelerate particles, say by curvature acceleration or parallel electric field, you create particles with very small pitch angle. But if you allow for pitch angle scattering, particles can also efficiently interact with magnetic mirrors. So, for example, for small pitch angle, particle just can go through the mirror, but for a larger pitch angle, it can be reflected from this mirror. Therefore, we believe that what if we consider a model where we can accelerate particles with a curvature or by mirrors, and then we kind of have pitch angle scattering, and particles with larger pitch angle scattering are accelerated more efficiently because they can interact with magnetic mirrors. Particles with small pitch angle are not accelerated by magnetic mirrors, just fly through the system, only feeling curvature acceleration, possibly, right? What if we construct a simple stochastic model, saying that magnetic moment of particles can be increased due to interaction with some structures, and can also change its direction due to pitch angle scattering. So this is the simplest stochastic model. So we say that magnetic moment over time is proportional to the amplitude of the magnetic moment itself, because we need to have kind of log behavior, and some scattering vector, which is a random vector, say Gaussian vector, which has kind of white noise, kind of uncorrelated, kind of random noise, right? So this picture immediately provides the right scaling of delta p squared, which is delta gamma squared proportional to gamma squared. Yes, that would follow, that would be consistent with log normal distribution. But then we use this equation as a Langevin equation and write the corresponding Fokker-Planck equation for the distribution function of plasma particles. So once again, this is a cartoon model. I don't claim that I derive it from some first principle. It's just I try to kind of incorporate the ingredients of energy increase and pitch angle scattering, but do it in the most random fashion without assuming anything about anisotropy of this process, so just do it randomly. So this is the equation which I get. I can rewrite this equation assuming that my distribution function depends, assuming that there is some guide field, some preferred direction, so it depends on the magnetic moment, and on the mu here is not a magnetic moment, but pitch angle, cosine of the pitch angle. So I write this diffusion equation, separating this, in moment and pitch angle. And then we say that particles whose pitch angle is smaller than, say, some parameter mu naught, which depends on the strength of magnetic mirrors, just go through. They're just lost. And particles whose pitch angle is larger than mu naught are scattered. So basically, I impose the boundary condition on this equation that at some mu naught, my distribution function is 0. But larger than mu naught, I evolve it according to this equation. We immediately see that it looks like a leaky box. So this term describes dissipation. For kind of small pitch angle, number of particles decreases. And one can solve this equation. One can find eigenvalues of this equation. They look like that. So depending on the strength of on the fluctuations of magnetic field, which are given by large-scale conditions. You can calculate this alpha parameter. And I think my last slide is we compared with simulations with different delta B over B naught, different values, calculated this alpha from theory, and compared with what you measure in numerical simulations. So when we see that in the delta B is close, when B naught is smaller than delta B, it kind of saturates at about 1.8, negative 1.8 or negative 2. But when guide field becomes stronger, it becomes steeper. And when it becomes too strong, we simply cannot measure it any longer because it somehow transfers over log normal out of power law. So, OK, so that's my last slide and just simple conclusions. So Alfvénic turbulence has certain similarities to the non-relativistic case, in relativistic case, but also have some important, maybe with fundamental differences. So in simple model for acceleration mechanism, which as now we suggest depends strongly on what is happening to the adiabatic invariant and to the pitch angle, may provide at least good qualitative description for the numerical results. Thank you.